Hey guys, welcome back to Chapter 3, Section 3.2, Measures of Variability. In the last lecture, we covered the range, and now we're going to move on, and we're going to look at the variance and the standard deviation. So let's start with the variance, specifically the variance of a population. Now, the variance, in addition to the range, is another method of measuring the variability or the spread of a set. So first, we're going to assume we're working with a population, and we're going to look at the formula for the population variance. Now, there's going to be a couple of new symbols that I'm going to introduce. We have sigma. So let me write this down. So this guy right here is called sigma. And we use sigma squared to represent the population variance. The population variance is equal to the sum of x minus mu squared divided by capital N. So let's talk about this formula for a minute. So let's think about what we're doing here. So we're taking the sum. So remember, this is our summation symbol. So we're going to sum up each difference between the data value and the mean of the population squared. So we're going to take each data value minus the mean and square it. We're going to sum up all those squared differences for each data value, and then we're going to divide by the size of the population, and that would give us our population variance. Now remember, realistically, we're usually working with a sample. Because remember, it's usually impossible or impractical to get data from the entire population. So most of the time we're working with a sample. So let's talk about the sample variance. Now we need a different symbol. We can't use sigma squared because that's the variance of a population. So we use S squared to represent the variance of a sample. And the formula looks very similar to the formula for the population variance, but you'll notice a couple of differences. So the numerator is equal to the sum of each data value x minus x bar, because remember, x bar is the mean of a sample. So we're going to take each data value minus the mean and square it, very similar to what we would do if we were calculating the population variance, just different symbols. But now we're going to divide by sample size minus 1. So remember, lowercase n is the size of the sample, and we're going to subtract 1. So what the variance lets us do is it lets us measure the variability of a set, and we're going to use all the data values in the distribution. The range, so remember the first measure of variability that I went over in the last lecture was the range. And the range only used two data values in the set, the two extreme values, the largest and the smallest data value. And it doesn't use the rest of the data values in the calculation. Therefore, we said it's not an adequate way to completely measure or distinguish between the variability of two sets. So what we're trying to do now is we're trying to come up with a measure of variability where we're going to use all the data values in the set. And what we're going to do is we're going to see the difference between each data value and the mean, and we're going to square it. And I'll talk about why we're going to do that in a minute. Sum them up and divide by either n or n minus 1, depending if we're calculating the population variance or the sample variance. So let's do an example. Before we talk about, so notice I'm skipping over the population and sample standard deviation. We'll get to that in a minute. So what I want to do is let's calculate the variance in example 7 of this sample data. So it says the following sample data represents the hourly wages of 5 employees of a small bakery in Boston. So these employees make $6 an hour, $10 an hour, $9 an hour, $12 an hour, and $8 an hour. So these are the hourly wages for a sample of 5 employees. So we want to compute the sample variance. Now we're working with a sample, so the sample variance is equal to the following, right? The sum of each data value minus the sample mean squared, and we divide by sample size minus 1. So let me write this formula down. And I set up this little table to help us use this formula in a nice systematic way. So S squared is equal to the sum of each data value minus the mean squared, and we divide by n minus 1. So we're going to do that for this data set of 5 numbers. So why don't we list the 5 values in our set? So we have 6, 10, 9, 12, and 8. So I'm going to call this column X because those are my X values. Now, in order to compute this formula, I have to take X and I have to subtract X bar from each data value. So why don't we calculate the sample mean? So we have it. So what is X bar in this case? So what is the sample mean for these 5 hourly wages? So you guys could pause here and you could find the mean of the numbers 6, 10, 9, 12, and 8. And when you do that, you should get a mean of $9 an hour. So X bar is equal to $9 an hour. So now what I want to do is I'm going to create a column for X minus X bar because that's going to be part of my numerator. So what we're going to do is we're going to take each data value and we're going to subtract the mean. So we want to see how far away each data value is from the mean. What's that difference from the center? So my first data value is 6. So I'm going to take 6 and I'm going to subtract X bar, which is the sample mean. So 6 minus 9, that's going to be -3. Now I'm going to take my next data value, which is 10. I'm going to subtract the sample mean of 9 and we get 1. Then I'm going to take my next data value, which is 9. I'm going to subtract the sample mean and I'm going to get 0. Because there is no difference, right? 9 from the mean of 9 is a difference of 0. Now I'm going to take my next data value, which is 12. I'm going to subtract 9 and we get +3. And then my last number in the set is 8. I'm going to subtract the mean and we get -1. So these values in this second column represent the difference between each data value and the mean. So think about what we're trying to do. We're trying to figure out what is the average spread of my data set? What is the average variability? So it would make sense right now to try to average out all these differences, right? To add them all up and maybe divide by however many differences there are. But look what happens when I sum up this column. So if I were to sum up -3, 1, 0, 3, and -1, the sum of all these differences is going to equal 0. And the reason it equals 0 is because, look, I have opposites in here. I have a -3 and a +3. I have a 1 and a -1 and a 0. So when I sum up opposites, I'm going to end up with 0. This is always going to happen no matter what data set you're working with. If you were to take each data value and subtract the mean and sum up all those differences, they're always going to sum to 0. So that's the reason why we're going to square all these differences. That's why when we look at the formula, we see X minus X bar squared. Because we know if we sum them up without squaring them, because we have these opposite numbers, you know, half are negative, half are positive, it's going to sum to 0. So what we're going to do is we're going to take each difference and we're going to square it. So we're going to take -3 and square it, and we're going to get +9. And notice I'm putting parentheses around the -3 because I want to square the entire entity, including the negative number. If you were to plug -3 squared in the calculator without the parentheses, you're going to get an answer of -9, which is not the same thing. So parentheses play an important role here. Next, we're going to have 1 squared, which is 1. Then we're going to have 0 squared, which is 0. Next, we're going to have 3 squared, which is 9. And then last, we're going to have -1 squared, which is +1. So look, I don't have any negative numbers in this column anymore because we're squaring all of these differences. Whenever you square something, whether it's a positive number or a negative number, the result's always going to be positive. So when we go to sum up all these squared differences, we never have to worry about it summing to 0. So we're going to take now the sum of x minus x bar squared. So now we're going to add up all these squared differences. So 9 plus 1 plus 0 plus 9 plus 1. And that's going to end up being 20. So that's the numerator in my formula here for the sample variance. The sum of x minus x bar squared in this case is equal to 20. And now what we have to do is divide it by n minus 1. And remember, n is the sample size. So n in this case is 5 because we have 5 hourly wages here. So we're going to divide by 5 minus 1, which is 4. And 20 divided by 4 is 5. So my sample variance as squared is equal to 5. But let's think about the units right now. Is that I know my data is in dollars, but is this $5? Let's think about this for a minute. Think about what we did to every difference that we squared, right? So we took each data value, we subtracted the mean, and we squared it, and we summed them all up. So these are all square differences. So my unit actually is in square units. So this right here, this 5, this is really 5 square dollars, which kind of is weird, right? Because we typically don't talk about money in square units. And it's hard to relate it back to the original data set because the original data set is not in square units. So we always have to remember that the sample variance or the population variance is always in square units. And it's hard to relate that back to the original data set. And I have that here. It says this right here at the top of the page that the sample I'm sorry, I meant to go a little bit higher. Right here. The sample variance is a measure of variability that is determined using all of the data values of a distribution and is used as an estimate of the population variance. But one disadvantage of the variance is that the variance is measured in square units, while the data values within the distribution are not measured in square units. Since the unit measurements for the variance and the data will always be different, it's hard to interpret and relate the variance as a measure of variability to the data values within the distribution. So typically what we do is we unsquare this value, or we take the square root, right? That's how we unsquare something. So this brings us to the standard deviation. So the standard deviation, whether it's the population standard deviation or the sample standard deviation, is just the square root of the variance. So if we take the square root of the variance, we're not in square units anymore. And now it's going to be easy to relate this measure of variability back to our distribution. So the population standard deviation is just going to be the square root of sigma squared. So that's going to be sigma, and that's equal to the square root of x minus mu squared divided by n. And if we're working with sample data, then the sample standard deviation is the square root of the sample variance, or the square root of s squared. And we get s. So s would be the square root of x minus x bar squared divided by n minus 1. So now what I want to do in the second part of this question is compute the sample standard deviation, and we'll interpret it. So remember what we just said, the sample standard deviation, which we call S, is equal to the square root of the sample variance. So it's equal to the square root of S squared, which is the square root of the sum of each data value minus the mean squared over n minus 1. And we got 5 for that, right? We got 5 square dollars as my sample variance. So we're going to take the square root of 5 in this case. And if we take the square root of 5, so we'll do this together in the calculator. So the square root, and to pull up the square root, we press second and then the x squared key. And we want to take the square root of 5. And let's round 2 places to the nearest penny or the nearest cent. So we're going to get 2.24 if we round this 2 places. So we're going to get $2.24. And now we're not in square units anymore because we took the square root. So now my units are dollars, not square dollars. So the sample standard deviation is equal to $2.24. Now, I think it's really important that we interpret this. So let's interpret what this means. What's $2.24? Well, look, we have a data set here of hourly wages, and the mean is $9 an hour, right? We calculated X bar to be $9 an hour. But there's deviation or variability from that $9 an hour, right? Not everybody makes $9 an hour. Some people make 6, some people make 10, some people make 9, some make 12, some make 8. The point is that there's variability from the mean, right? There's variability within this data set. Well, what is that average variability? Well, that's the $2.24. So the standard deviation tells us the average deviation or the average variability from the mean of the data set, which in this case is 9. So in words, what we would say is the hourly wages of the employees in this bakery, they vary, right? The wages vary. Not everybody makes the same thing, so they vary. But the key is on average. This is an average deviation or variation from the mean. So the hourly wages of the employees in this bakery vary on average about $2.24. But what is it varying from? Well, from the mean of $9 an hour. So that's how we interpret the standard deviation. The standard deviation is the average deviation from the mean. So we would say that the hourly wages of the employees in this bakery vary on average $2.24 from the mean of $9 an hour. So think about how we calculated the sample variance and then the sample standard deviation. We had to use this formula, right? And we made this table to kind of help us, systematically sum up all these square differences, and then we divided by n minus 1. This wasn't really so bad because there was only 5 data values, but what if there was 50 data values? This would be a lot of work, right, to plug into this formula. So what I want to do now is I want to show you how to get the sample standard deviation and the population standard deviation from the calculator. It's going to be much quicker. So the point is, you don't have to use this formula. I like to introduce this concept using the formula because I want you to see how we use and interpret the formula. And I think it makes sense in the interpretation. But going forward, I don't want you to spend all this time trying to calculate these things by hand. I want you to take advantage of the technology and I want you to use the calculator. So let's get this same answer, this $2.24, the sample standard deviation, but now using the calculator. So your steps are right here on the next page. So using the calculator to get the standard deviation. So the first thing we have to do is put the data into a list. So if you want, you could pause here and I want you to enter these 5 hourly wages into your calculator. So once the data set is in your calculator, it's actually the same steps that we use to get the mean and the median. You're going to press stat, we're going to go over to calc, one variable stats, and then we're going to enter the list number that you used, and then we're going to calculate. So we'll do this together. So let me share my calculator. I already have my list in here. So I entered those hourly wages into list 1, my 6, 10, 9, 12, and 8. So what we're going to do is same that we did before, the one variable stat in the previous lesson. So we're going to press stat. We're going to arrow over to calc. We're going to choose option 1, which is one variable stats. Make sure you put the appropriate list. So mine was in L1 this time. We're still leaving frequency list empty, and we're going to calculate. And we're familiar with this input, right? We've done this a few times before. But now we're looking for the sample standard deviation, which in the calculator, it's the fourth one down in the output. It's S with the little X next to it. By default, the calculator uses a little sub X, but it's the same thing as S, the sample standard deviation. And you'll see it's equal to 2.236067977. That's the sample standard deviation. And if you want the population standard deviation, which is sigma, but in the calculator, it's sigma with a little sub X next to it, that would be 2. But in this case, we were assuming this was sample data. So I wanted you to calculate the sample standard deviation S, which is equal to 2.24 if we round 2 places. Now notice the calculator doesn't give you S squared or sigma squared. It doesn't give you the variance. But you could easily get the variance by squaring the standard deviation. So let's do one more example and then we'll wrap up this lesson. So let's look at example 8. So for example 8, we have the top speeds in miles per hour for a sample of 5 new automobile brands are listed below. Calculate the sample variance and the sample standard deviation of the speeds. So we have 5 speeds here. So rather than calculating the variance and the standard deviation by hand, let's take advantage. We'll use the calculator. So pause here, enter these 5 data values into a list in your calculator, and then we're going to do a one variable stat, just like we did for the previous example. Now I already have my list of speeds in my calculator. I have it in L2, list 2. So I'm going to press stat. We're going to arrow over to calc and one variable stats. But now I have to change my list to L2. Leave frequency list empty. And then we're going to calculate. And for this one, we want to calculate the sample standard deviation and the sample variance. So we're assuming that we're working with sample data. So remember, the calculator only gives us the standard deviation. It doesn't give us the variance, but we could calculate that. So my sample standard deviation in this case, S with the little X next to it, is equal, if we go 2 places, to 37.18. So let's write that down. So 37.18. So S, which is the sample standard deviation, is equal to 37.18 miles per hour. So that's my sample standard deviation. And I'm just going to make a little note that from now on, when I write SD, this just stands for standard deviation. This way we don't have to write it out every single time. Now we also want the sample variance. Calculator's not going to give us the variance, but the relationship between the variance and the standard deviation is that the variance is the standard deviation squared. Remember, variance is in square units. So if we want to calculate S squared, I'm going to take the 37.18 and I'm going to square it. So if we square 37.18, now your squared key is halfway down the first column. You could see it in red here, x squared. So 37.18 squared is going to be about 1382.35. So we'll write that down. So this is equal to 1382.35, and my units are miles per hour squared. So we're in square units. So this is the sample variance. And even though I didn't ask you to do this, I want to interpret. So again, let's interpret, and I'll do this in red, the standard deviation. So what we could say is that the speeds vary, right? Because these speeds are varying. They're not all the same, right? They're varying. So these speeds vary on average 37.18 miles per hour from. Now remember, what are they varying from? Well, they're varying from the center or the mean. So they're varying from the mean of, and let's go back and look at what the mean was. We already have this set or this list in the calculator, right? So let's go back and let's do a one variable stat since I got it off the screen from before. So I'm going to do one variable stat again. And the mean in this case is 153, right? You see X bar is equal to 153. So we're going to vary on average 37.18 miles per hour from the mean of 153 miles per hour. So X bar in this case was 153 miles per hour. So the average deviation from the mean is about 37.18 miles per hour. And that's how we interpret the sample standard deviation. In the next lesson, we're going to do another example and I'll do a little bit more review on the variance and the standard deviation.